Thank you very much. So, I am sorry to speak for so many hours today. It is as hard for me as it is for you. Maybe it's a little harder for you. In the morning, there may be no Dirac operators. There will be a Dirac operator in the afternoon. These lectures will be independent of the lectures from 2 weeks ago and 3 weeks ago and 4 weeks ago. It's the same subject, and I will make the lectures independent by repeating some of the things that I already said. So I will begin by repeating. It's always good, at least for me, to repeat after I say something 4 or 5 or 6 times. Then I begin to learn it. And so maybe it's the same for you. If you hear something 4 or 5 or 6 times, maybe it will help. All right. And so let's think about what we have been doing from a slightly different point of view. Story so far. We've been studying these real reductive groups. It just means, I said it many times, it's a closed subgroup of matrices with only finitely many components, almost connected subgroup. GLNR. With this crucial condition that the space is closed under the transpose operation. Like that. The issue of connectivity of the group is a very complicated one. It would be really great only to ever have to think about connected groups, because there are details which are significantly simpler for connected groups. But as soon as you start to think about connected groups, you find there are some disconnected groups also that are very important. They arise as subgroups. So you have to consider disconnected groups. Sorry. And it's always a detail to worry about. I'll say more about this in just a moment. If you are given such a group, it may not be in, so to speak, convenient form to begin with. You can make it slightly more convenient. You can make G sit inside of GLNR in a slightly more convenient way. As follows. What does convenient mean? Anyway, up to conjugacy by an element of the orthogonal matrices. In other words, after changing the bases on these matrices, we can guarantee that this thing, which is just G intersected with the positive diagonal matrices, each entry should be positive, in other words. We can guarantee that this thing has the following property. It's maximal among all subgroups consisting of positive definite matrices. So let's say a maximal positive definite subgroup. If you have a group of matrices consisting only of positive definite matrices, or for that matter, self-adjoint matrices, then it's easy to see it has to be abelian. So this is an abelian group. Any such group consisting of positive definite matrices is abelian, and of course it can be simultaneously diagonalized by linear algebra. If you have a commuting collection of symmetric matrices, you can diagonalize them simultaneously, and so up to conjugacy, you can put them all in diagonal form. In other words, if you start with one of these things, you can diagonalize it and obtain this good situation. And I pointed out, in fact, we proved it, didn't we, that this object, this maximal positive definite subgroup, it's not unique, but it's unique up to conjugacy by an element of K. It's unique up to conjugacy inside of G. So it's not exactly a canonical thing, but it's pretty close to a canonical thing. All right, and it's a lot of what we want to do has to do with this equation here, that everything in G can be written as something in K. Oh, I forgot to say what K is. Up here. It's just the intersection of G with the orthogonal matrices. Everything in G can be written as something in K, times something in A, times something in K again. Okay. So A tells you how non-compact the group G is. If A consists of one element, which it could, then clearly G is compact, if and only. And A gives us a way of measuring the complexity of G.
A is abelian, right? A is abelian.
Can you say again?
Abelian type 2?
It has to be abelian, because if you take A times B, it's a group. So again, it has to be in the space, and by hypothesis, it's symmetric. So A times B is equal to A times B transpose. But A times B transpose is B transpose A transpose. And B transpose is B, and A transpose is A. So AB equals BA. So it's always abelian. And the convenient way of measuring, from our point of view, the complexity of G is by no means the only way. Roughly speaking, I want to just calculate the dimension of A. A is isomorphic to a vector space, and as it happens, by taking logarithms. And roughly speaking, I just want to take the dimension of A. But a group would not be very complicated if it was just isomorphic to Rn. In other words, if it just consisted of positive diagonal matrices, you would not want to call that a complicated group. Positive diagonal matrices are pretty easy. So let's divide out by that part of A, which sits in the center of G. Like that. And we'll call the result the rank or the real rank of G. Okay. If this rank turns out to be 0, then G is just compact. Well, not exactly just compact, but compact times the Cartesian product of a compact group and an abelian of a vector group. So it's very easy. These are the easy groups, we hope. And a lot of representation theory in this world goes by induction on the rank, the real rank as it's also. Right. So rank 0 is supposed to be elementary. We'll talk a bit about rank 0 today, and then rank 1, not so elementary anymore. Rank 2, actually rank 2 is as hard as anything. Yeah, we hope to theoretically understand groups of rank 2 by first understanding groups of rank 1, and so on and so forth. All right, very good. Do I want to say anything else? Oh, let me say one more thing.
Sorry,
yeah, sure.
Question. Is the dimension in what sense?
This is a Lie group, so the dimension as a manifold. In fact, A is always isomorphic to the following thing, which is just the set of matrices which exponentiate into A, T, like this. And it's isomorphic here, of course, just via the exponential map, or in the other direction by the logarithm. So A is always a vector space, okay. And the intersection of A with the center, if you think about it, is also always a vector space. So this thing that I'm taking the dimension of is a real vector space. If you don't like manifolds or Lie groups, it's just a vector space. Right? Oh, yeah, I was going to say one more thing, but now I've... oh, yeah, I remember. I remember what I wanted to say. Concerning this center and this fellow here, it's always the case that G, I think I mentioned this before, but I'll say it again. Let's do it like this. You can always split off this part of the group It's a boring part of the group. So S is what I was previously just discussing, which is this thing. This is the part of A which has to sit in any choice of A. It's invariant under the different choices of A. And there's always a complementary group, so that this has to be a Cartesian product of groups, because, of course, this thing is central. And there are various ways of describing this canonical quotient, but a factor. But one way is to say it's just the intersection, the mutual kernel of all homomorphisms, group homomorphisms from G into the reals, or use these things usually arise multiplicatively like that. So, for example, if G is GLNR, perfect example, then M is the set of matrices whose determinant is plus or minus 1, sorry. I'll fit that in. And S, this split component, as it's called, is isomorphic to R plus by the determinant. So this is a very fortunate thing about groups over the real numbers. They fall apart into these two easy pieces. And it means that, and one more thing, because this hypothesis is going to arise in just a moment. I'll reveal this again in a moment. Once you've done this, the center of the result is compact. So that's a circumstance that will be significant later on. Okay. I thought we didn't do this before. Let's just take a look at some examples. In fact, I can give you the complete list of examples, more or less, and let's just do it for fun to illustrate some point. I'll try and keep this on the board for a little bit. So what I'm going to do is write down the so-called classical groups. So these are groups which are simple. They're not even locally the products of other groups, and they are linear according to our definitions. We want them sitting inside of Rn. And what else about them? Oh, that's it, yeah. Simple linear. Oh, and they're the easy ones. There are classical groups, and then there are exceptional groups. I'm not going to tell you about the exceptional groups. Life is too short. But let's just make a little list. It's not the point I want to make is that when you study these groups from a certain point of view, you're only ever doing linear algebra, because all the groups are given in some linear algebraic way. We know what SLNR is. What about this fellow here, SOPQ? I think in my world, we'll always make P be bigger than Q. So this is just matrices which preserve quadratic form of the right type. And Q here, let's stick it here. Now, for me, if we want this hypothesis to hold, maybe the best way of writing Q is like this. We'll take the identity of size P minus Q, the identity of size P minus Q, and down here we'll put the identity of size, do that right? P minus Q, yeah, oh. So what's the remaining size? So now it's, I can't even tell you what it is. Ah, no, it's the identity of size Q, that's where I'm confused. And then the identity of whatever remains, which I guess is Q minus Q. So these are P plus Q dimensional matrices. And there's a reason for writing down this list. You can do the same thing using complex matrices instead of real matrices. And you can do the same thing using quaternionic matrices instead of complex matrices. This is the conjugate transpose. The quaternions have their own, how should we write it, some diamond or something, their own transpose conjugation operation. So I'll put in a diamond here. So here we're using complex matrices. Here we're using quaternionic matrices. can do something similar, not with symmetric forms, but with anti-symmetric forms, skew forms. So you could look at real matrices, which we call this S for symplectic. Oops. Like that. And we're pretty much done. Not much else you can do. A couple of other interesting things you can do. I thought it's worthwhile explaining what at least one of them is. The other one I'll leave. The other one I'll leave to your imagination. There are two other families of examples like that, and that's, if I haven't forgotten anything, that's the, more or less the complete list of groups. There are also groups where you just take all of these fellows and you complexify these groups as a complexification operation. So for example, you can deal with SLN-C, and you can deal with SOPQ over the complex numbers. It just means you use exactly this equation with the transpose, not the conjugate transpose, but the matrices now involve complex entries rather than real entries. So that defines the complexification of this group, and the same for all of these. And so you have to consider those. Oh, and you have to consider compact groups too, classical compact groups. And that's a complete list. Maybe I'll just stick it at the bottom here. Complexifications, complexifications, and what are called compact forms. Some of which are included in here, not all of them. And I just wanted to say a word about one of these, just for fun, just to think about some small detail. Because it introduces an idea that will arise in the afternoon anyway. And so let's just go ahead and do this. You could just write down the definition of this, but I'd rather explain to you why the definition should give rise to an interesting group. So suppose you start with the following inclusion. If you have a matrix, which is a unitary matrix of size n, you could think of it as a real matrix of size 2n by 2n, because every complex number is like a little 2 by 2 matrix of real numbers. And so you can always embed un inside of the orthogonal matrices. And when you do that, the determinant in the real sense is always the modulus squared of the complex determinant. So you always get a determinant 1 matrix in this way. And we haven't really talked much about Lie algebras, but everyone knows that there's a corresponding Lie algebra, un, and of course it's now embedded inside the Lie algebra SON, like this. In fact, the big Lie algebra is equal to the little Lie algebra direct sum a complement, P, like that. There's an involution on orthogonal matrices whose fixed set is exactly the unitary matrices. And the involution is, if you like, multiplication by I. If you have a complex matrix with complex entries, then these are the complex linear transformations inside of the orthogonal transformations. And to be complex linear, it just means you commute with multiplication by I. And so there's an involution on all orthogonal matrices. Excuse me, that should have been 2n. There's an involution, and that should have been 2n. Oh dear. Finally, that should have been 2n. My apologies. There's an involution on SO2n, a Lie algebra automorphism of SO2n of order 2, and its fixed algebra is exactly un. And this P that I've written down here is the -1 eigenspace of that involution, and this is what this eigenspace decomposition is called the Cartan decomposition. Now you can do the following thing. You can do the following thing. If you have a Lie algebra with of real matrices with a decomposition like this given by an involution, you can build a new one. by taking all of the old matrices that you had in UN and just looking at the square root of -1 times the matrices in P. If you take the Lie bracket, the commutator of two matrices in P, then you get a matrix in U. That's a consequence of the fact that this is a decomposition coming from a Lie algebra automorphism. And so if you multiply all of the P matrices by the square root of -1, when you take the bracket of two P matrices now, after you've multiplied them by the square root of -1, their commutator bracket lies in here, but it's minus what you had before. So you change the Lie algebra structure by multiplying by the square root of -1 here. Okay, and when you do that, you no longer have the Lie algebra of a compact group. You have the Lie algebra of some other group, and it's the group in question to which this exponentiates is this fellow here. So you can put it in another way, so going in reverse. You could say that SO2n is the compact form of SO star 2n. So this is a non-compact group of matrices with the property that its Lie algebra looks like this. And if you multiply by another square root of -1, you cancel out the first one, you get the Lie algebra of skew-symmetric matrices. So for every one of the groups that we're talking about, you can, if you like, compactify the group by this square root of -1 trick, and you can uncompactify it if it was already compact by putting in a square root of -1 too. So there's a nice backwards and forwards motion between non-compact groups and compact groups given by this little rotation trick here, this sort of wick rotation trick. And we'll use that later on, so just for fun, I thought I'd tell you about it now. And now that we've done all of that, we have a complete list of all of the groups. And all of these groups have compact center. In fact, they all have finite center. And this rank that we're talking about here is, well, in this case, n-1. In this case, it's q. And in this case, it's q. And in this case, it's q. And in this case, it's n. And in this case here, it's half of n. Like that. And in this case, I can't remember. The other one, SU, maybe n-1. Not totally sure about that. Oh, and finally, for these complex groups, it's equal to the complex rank, if you know what that is. And then finally, for compact groups, it's equal to 0. All right, that was just for fun. As we did before Golden Week, we have to go slowly on these days when there are so many hours so that we don't tire ourselves out. And, so there you go. So it turns out you can classify the groups that we're looking at, and the fundamental building blocks are exactly the ones I've written down, plus a handful of exotic groups with well-known names, E and G and F and so on, and that's it.
So for those PQ groups, group P doesn't enter into the rank.
That's correct, yeah. So SON1, for example, has rank, maybe I should have said SOP1, has rank 1 all the time. So these groups are small from a certain perspective. Of course, their dimension is very large. Their complex rank, the rank of the complexification, is also very large, roughly speaking, P over 2 in that case. But for the particular strategy we have in these lectures to understand unitary infinite dimensional irreducible representations, the relevant way of judging the size of the group is this funny way here. So SON1 is a small group from the point of view of this type of theory, although it's large from many other perspectives. Yes, all right. Let me see what else I would like to say. Oh, yeah. So the crucial construction that we discussed last time was the following, that if you take an H in A, this was the set of matrices which exponentiate into big A, into the positive diagonal matrices. So these are the diagonal matrices inside the Lie algebra of G. And if you have one of them, we defined, so to speak, on speculation, the justification came later, but we defined an associated group N, which was just the matrices G, with the property that when you exponentiate them, excuse me, when you not exponentiate them, conjugate them by this one parameter group, like this, then the action of the one parameter group is contracting in this way. And while we're at it, there's an L, which, for which this one parameter group is centralized, like this. And these tend to look like block upper triangular matrices, as we discussed in the case of N, and block diagonal matrices in the case of L. If you happen to have an H whose diagonal entries are non-increasing, then N is always an algebra of block, always a group rather of block upper triangular matrices with identities down the diagonal, and L is the corresponding group of block diagonal matrices. So we always define these things. And you always get something. If, at least if G is connected and has compact center, you always get something interesting here. If you happened to have a group which did not have compact center, and if you happen to have an H, choose an H, which exponentiated into the center, then of course you wouldn't get anything in E, because this would just be G, and G cannot converge to the identity unless it is the identity. So this would be a rather trivial construction when G had some non-compact center, and so that's the reason for including compact center, and connectedness we'll get to in just a moment. Then, if you happen to have ended up with the trivial group, it means you started off with the trivial matrix. And L is always smaller than G. If L is equal to G, then it's because H is 0. So whenever H is non-zero, you get something smaller and, in principle, simpler. In fact, you could replace this by saying that the rank of L is equal to the rank of G. If this operation of passing from G to L doesn't decrease the rank that we've defined, then it's because you did something stupid. You chose the trivial one-parameter group. Otherwise, L is definitely simpler, according to our standards of simplicity, definitely simpler than G.
Which is what kind of space?
These are all Lie groups, and in particular manifolds. And so I'm encouraged, well, I'll draw a picture in a moment of not of these spaces, but of the related homogeneous spaces. So I do want to think about these things geometrically, but they're manifolds, and submanifolds of the space of all matrices, of course. All right. So far, so everyone's awake and alive today, asking questions. Oh, yes. Still early. Oh, yeah, I mean, I know that after lunch, you guys are going to be like this, and the only person awake is going to be me. Yeah, get your questions in now, yeah. When the last person falls asleep in the afternoon, I will just leave. We'll switch the video to a still frame and just... Yeah, I remember what I wanted to say. So we'll keep the little list here for a moment, but let me remove the discussion of SO star to N. I don't know how to say this. SO star to N, I don't know how you say that in English, let alone Japanese. So we did something last time, which I'm not going to repeat, except in its barest outlines. just to emphasize a slightly different perspective on what we said, we constructed some object from functional analysis. And so it has a name, and this is the name. It's a space, it's a completion in the sense of functional analysis. There's a norm and then you complete. It's a completion of the space of functions on G mod n, just like L2 of G mod n is a completion. And you're supposed to think of this as pretty much the same thing as L2, except you change the norm to get a more convenient one. On L2 of G mod n, it's a Hilbert space. So there's a norm coming from an inner product, and that inner product is scalar valued. Here there's some sexy inner product which is valued in, so what is the C-star module over? Valued in this C-star algebra. And we built a star. I think there are too many syllables in that word. Try it again. Homomorphism. We built a star homomorphism on the C-star algebra of G. Now, it's a slightly complicated thing. Concepts are stacking up one on top of another like this. We have this module, which is not exactly a Hilbert space, but it is inspired by a Hilbert space. And there's an algebra of operators on this module, even though I'm calling them by the symbol we use for compact operators. They're not exactly compact operators in the sense of Hilbert space. They're another type of compact operator. And we built such a map. But what happens is that this thing here is a C-star algebra which is Morita equivalent to just the C-star algebra of L. And we discussed the category of non-commutative topological spaces last time. And what you're supposed to think about this as is just, all I'm about to write down is a definition. We defined such a morphism to be an example of a morphism It's not exactly a C-star algebra homomorphism between the C-star algebras I'm writing down. It's what's called a correspondence. But you're supposed to think of this as a generalized homomorphism from here to here in this category that we discussed, the category of non-commutative topological spaces. This was a category whose objects were C-star algebras. And the morphisms were exactly like this. The morphisms always were star homomorphisms from the beginning C-star algebra to the compact operators on a Hilbert module over the end C-star algebra. And we discussed the justification for this, but we called this a morphism in the category of non-commutative topological spaces. And you can compose these. It really is a categoriance. If you're a topologist, you would call such a thing a transfer map. If you're a representation theorist, your terminology would be a little bit different. You would call this, it's a bad name, but you would call this parabolic induction. And in either case, what it is a mechanism. It's a mechanism which takes representations of L. Look at this bottom line here. Pretend that this dotted arrow really was a star homomorphism. Then each time you had a representation of this C-star algebra on a Hilbert space, by composition, you'd get a representation of this C-star algebra. Well, that property of being able to transfer representations from L to G also works for these morphisms in the category of non-commutative spaces. It also works for these correspondences. So if you're a C-star person, you would call this a correspondence. No, you wouldn't use those words. And yeah, so this is a way of making representations of L into representations of G. And it happens to coincide with what the representation theorists call parabolic induction. Okay. And it's a very good map. It has the following property. thanks to the big theorem that we were discussing last time, which I'll remind you about, this operation of transfer, it does not send irreducible representations to irreducible representations, but it's not too bad. It sends irreducible reps to completely decomposable representations of G, or of the sister algebra G. It means representations which discretely decompose into a direct sum of irreducible representations. You're not guaranteed that sort of thing in infinite dimensions, but here, as a result of the theory, you do get this. In fact, a little more work shows that these are always finitely decomposable. And in some cases, transfer takes irreducibles to irreducibles. This works, for example, for complex groups. And a few isolated cases, for example, this is the case for GLNR. This so happens to be the case for SL odd, SL3R, SL5R, and so on. There are a few examples like that. I just want to give you the sense that this is really creating irreducible representations of G, and when it's not creating irreducible representations, it's almost creating irreducible representations. These representations you get by transfer are almost irreducible. They break up into, as it happens, finitely many irreducible parts. That's quite easy to check. Generically, by the way, generically irreducibles go to irreducibles, and then, as I've written here, sometimes it's the case that irreducibles always go to irreducibles for certain particular groups. So we had this construction, and the value of the construction was that it almost accounts for everything. And one of the things I want to do today is say more precisely when it does account for everything. So there was a wonderful theorem which says that if you do it like this, make it look better. It says that if you look at the part of the C-star algebra which is not seen by these transfer maps. So when I talk about the kernel here, I mean the kernel of the associated actual honest star homomorphism up here. Then that's contained in a very small part of the C-star algebra of G. So this is a main theorem that we were discussing before Golden Week. And this is correct as it stands for compact center G, which are also connected for reasons related to what I was saying up there, sort of thing. Then this is contained in a direct sum like this. Indexed by some discrete collection of irreducible representations. First of all, this is what the C-star algebra is. It's called a C0 direct sum. Basically, the algebraic direct sum. These are all ideals, complemented in ideals, in fact, inside of C-star of G. So these are the ideals associated to what I call, following Bernstein, compact representations of G. And a representation was compact if indeed you could find some, oh, I missed a word, which I'll right here. Maybe I'll stick it here before we go along. The additional word I missed is admissible. It's hardly necessary to add this word because it's a fact that every irreducible representation is admissible. In fact, maybe that's all I'll say about it right now. And this ideal is defined sort of indirectly. In the definition of compact representations, it's assumed that there exists an ideal inside of the C-star algebra complementary with the kernel, so that the direct sum, the product of anything in here with something in here is 0, the direct sum is equal to the C-star algebra of G. So a representation is compact if and only if there is such an ideal as this, isomorphic to the compact operators, for which this is a true statement. And in the world of representation theory, these things are called a discrete series. These are all examples of, and it turns out, this is not so obvious, but it turns out to be true that these are exactly the irreducible square integrable representations. They're always definitely square integrable, but the converse is true as well. Okay. So all of the continuous representations are taken care of by this construction. And there was a picture to go along with this. My favorite picture these days. This is the picture for SL2 that you get by dividing G. Let me write this down in a different way. By this subgroup, the compact part of L times N. And this is a geometric space. This homogeneous space is a geometric space which is extremely close to another geometric space. The inside one here is G modulo K. If you have something in the C-star algebra of G which acts as the 0 operator under transfer, then that pretty much means, in fact, it exactly means that that element of the C-star algebra acts as the 0 operator on this Hilbert space. If it acts as the 0 operator on that Hilbert space, then it acts as basically the same thing as it acts as the 0 operator on L2 of this space. I'm going to change notation a little bit. If sigma was the trivial representation of K, then the functions in G which transform on the right according to sigma would just be the functions on G mod K, and the functions which transform on the right here according to sigma, restricted to this compact group, would just be L2 of this space. These two Hilbert spaces, together with their representations of G, are pretty much the same, because the underlying geometric spaces are pretty much the same. Not exactly the same, because down here they tend to differ rather substantially, but if you remove this compact part of G, then the two spaces are within epsilon, so to speak, of one another. So any operator which is 0 on here is going to be within epsilon of 0 here. And so the operator is going to be within epsilon of 0 up here on G mod K, and then something down on this compact region. What can it be on this compact region? It has to be a compact operator. What do compact operators have to do with compact representations? Well, you do the math and you find they have everything to do with compact representations. And so this picture is responsible for this theorem here. It's completely geometric. That's the point I want to make.
So sorry, so this picture sits where?
This picture happens to sit, this is a very special picture that you can draw for SL2.
Oh, I see. So this is SL2R.
In which case the picture lives, so to speak, in the algebra of G, which really is R3. So I'm able to draw it. These are adjoint orbits inside of inside of R3, inside of the Lie algebra G. When you pass, for example, to SL3R, then it's a more complicated story. And indeed, this space G mod K, there are different ways of going to infinity in G mod K, not just this way. And as you go to infinity in different ways, you have to use different homogeneous spaces G mod N to do the approximation that I was discussing, which is why you have to look at the intersection here over all possible ends. So we used some geometry to obtain a picture of a preliminary picture of the representations. Let me continue somewhere, maybe here. And we get the following theorem. So again, there's a version of this theorem without the hypotheses of connected and actually compact center is not even needed here, because I'm going to slightly reword the theorem. If G is connected, then every tempered irreducible representation, that is to say, irreducible representation of the C-star algebra, so the ones which are not obtainable by transfer from some smaller L are compact. That's what is being discussed here. And on the other hand, if you have a representation on L, L is a group just like G. It's one of these reductive groups. And if you have an irreducible representation of it, either it's compact, modulo center, or it's obtained from some smaller group for exactly the same reason. And what we find is that every tempered irreducible representation is either compact, well, the appropriate version of compactness for groups with non-compact center, compact modulo center, or is a component of a representation transferred by this process we were discussing, induced, if you like, parabolically from compact mod center representation. Somehow. So all the focus now, all of the attention is drawn to what are these compact mod center representations. Let me just remind you. Every G can be decomposed into something which has compact center, and then an S which is just abelian. And when I say compact mod center, this is not the politically correct way of making the definition, but a compact representation of G, excuse me, a compact modulo center representation of G is just a compact representation of M times a character, a unitary one-dimensional character of this abelian group. Compact modulo this central subgroup S. So that's just a hint at what the meaning of the various words is. And it's also supposed to suggest to you that in a certain sense, from now on, to understand representation theory, it's all about understanding these compact representations. That's not completely true. There are other issues too, but that's a major issue now to understand these representations. It's worthwhile noting something at this point, just to see what range of ideas we've been using up to now. We haven't really used any representation theory at all. What I'm thinking of here is the sorts of ideas that you see in the simple cases which are supposed to be included in our program. Every compact Lie group is a reductive group, and there's an elaborate theory of representations of compact groups discovered by Hermann Weyl, and we didn't discuss Weyl at all. And the other family of groups that are worth thinking about are the abelian ones, like this factor S here. And there's an important theory of representations of abelian groups, mostly summarized in the theorem of Plancherel, the Plancherel theorem for the Fourier transform. The only thing we've really used is geometry. G and these homogeneous spaces G mod n, etc. So if we're trying to understand representation theory, at some point we're going to have to talk about the Fourier transform, because in particular abelian groups are reductive groups, and at some point we're going to have to talk about the Weil character formula, the theory of compact groups, because in particular compact groups are reductive groups. We still have to talk about these things. We have, it's absolutely necessary that we bring these ideas into play. You can't avoid that unless you can miraculously, for example, reproduce the work of Hermann Weil just using pictures like that. We used one idea, one geometric idea. It turned out to be a very good idea. This is, by the way, the perspective of Joseph Bernstein, as I said before, not mine. We used one geometric idea, and it leads to a very good sense, overall sense of what representation theory looks like. There are discrete series representations, compact representations to worry about, and then there's this operation promoting a sort of a vaguer idea here of transfer, some mechanism of going from representations of L to representations of G. This is what people call parabolic induction. Okay. So far, so good. Oh, yeah, let's just, while we're at it, go back to this table here. As for discrete series, there's no one said that a given group has to have any discrete series at all, or indeed any representations which are discrete series modulo center. That's one of the things I want to talk about, probably in this afternoon. So let's just catalog what's going on here. All of these groups, as I said, have finite centers, so they're all have compact centers, and they're all basically connected. This one is not connected. It has two components, so, but it turns out to be that, okay. It has two components, but it's basically connected, and all of the others are connected. And as for these groups SLN, they only have discrete series when n is equal to 2. Well, I guess you could maybe say that the group SL1 has one discrete series. The trivial group, I guess the trivial representation of the trivial group is a discrete series, but nobody talks about that. As for these examples, it turns out most of the time you have discrete series to worry about. So in this situation here, the condition is that if and only when one of them is even, one of P or Q is even. So SO21 has discrete series, SO31 does not, for example. These ones here, yes, they always do. These ones here, yes, they always do. These ones here, yes, they always do. These ones here, yes, and no. Examples. Complex groups, no, and compact groups, of course, yes. But once in a while, occasionally, there are no discrete series at all, and then things become okay. So this is the sort of super big picture of representation theory. And this picture, by the way, is not sensitive to the underlying field. This is exactly the same theorem is true for exactly the same reasons in the, well, almost exactly the same reasons. You have to make some adjustments to the argument. In the case of p-adic groups, basically the same argument holds that proves this theorem up here. Okay, but now we want to get a little more specific. So here's a little philosophy. Before we go on. Which is supposed to guide us, and the philosophy is also supposed to unite these two fundamental contributions into one idea. that's important because we're dealing with groups which are a combination of non-compact abelian groups, the A, and compact groups, the K. So it's good to join those two things together, the Plancherel formula and Weil's work. The basic idea is that there's a duality between representations of a group and conjugacy classes. This is probably the fundamental idea of group representations. It's supposed to go like this. So what does this mean? It means, that is, an isomorphism between the following two objects: a space of functions on jihad, on the space of representations on the one hand, and the space of functions on conjugacy classes on the other. Functions on the irreducible representations, functions on the space of conjugacy classes. And the simplest case in the whole world is finite groups. If you have a finite group, no one is going to argue with you about what type of function to consider on a finite group. A function is just a function. And it's true that there's an exact bijection between functions on the space of irreducible representations, the set of irreducible representations, and functions on the set of conjugacy classes. First of all, it's known that there are exactly as many conjugacy classes as there are irreducible representations. This is something you prove in algebra. And secondly, there's an explicit map known, because if you have an irreducible representation, you can pair it with a function to obtain a number. Namely, you take, or if you like, maybe I'll put it this way. If I have a conjugacy class and an irreducible representation, I compare them to get a number. Namely, I just take an element from the conjugacy class, and I take its trace in the given irreducible representation, and that gives me a number. And if you think about it, that defines a sort of Fourier transform isomorphism from here to here. It is the Fourier transform if the group is a finite abelian group, finite cyclic group, for example. So this is an exact and precise isomorphism in which you relate the two sides through the idea of character of representation in the case of finite groups. And of course, this is exactly consistent with what Plancherel proved. Proved that if A is an abelian group, Rn, or just R, for example, then each time you have an L2 function on A, you can make an L2 function on the set of irreducible representations of A, which is the Contriagan dual group, just by Fourier transform. So the theorem, this principle, this philosophy achieves a precise form, at least if in the context of Hilbert space functions, L2 functions. And the other case that we need to think about are compact, let's say connected, and Lie, of course, groups. Oops. Okay. And I'm not going to say any more about the Fourier transform until later. But I do want to say something about the work of Weil, just to review or tell you. Let me see if I want to say anything else before I do that. I forgot to look at my notes. that? We did that? We did it. It's great. Ah, yes. Okay. Okay, so far so good. Any questions?
No.
No?
I'm just so happy.
Just so happy. You won't be happy this afternoon. Just wait until it's 3:30. You're going to be begging me to stop speaking at 3:30.
I'm going to, but I'm happy now.
Okay, let's say goodbye to this wonderful table. Goodbye table.
May I propose to take a break?
Oh, sure, sure. Yeah, we don't usually in this class, but we have guests. Yeah, by all means, let us relax, and there will be cocktails with... No cocktails. Still happy?
Yeah. I assume that that's 4 hours in one go, so, so I'm grateful to you. So,
yeah. By all means, let us take a break and resume at a time to be determined by Tsuyoshi.
Maybe we shall start from 11:10.
11:10, about Ancherel, although he was a very interesting man, it seems. But, let me move on to the work of Weil. Because we have to do it, because compact connected Lie group is a reductive group. And because what Weil did is so beautiful, and it's such a beautiful day, it would be, you know, on such a beautiful day, we cannot do ugly mathematics. It has to be beautiful. And this is very beautiful. Okay. So suppose G is one of these things. Compact connected Lie group. Like this one, for example. This, in the language that I was discussing earlier, this is the compact form of SLNR. You take SLNR and you make it into a compact group using the mechanism I described, or the reverse of the mechanism I described, inserting the square root of -1. Then from SLNR, it happens, you get SUN. It's kind of nice. All right. What is the starting point? Well, we had some philosophy, which is no longer on the board. And the philosophy says that to understand representations, you should understand conjugacy classes. So that's a good place to start. Conjugacy. And here there's a very beautiful and simple answer, namely, the conjugacy classes are labeled by a torus, U1 times U1 times U1, a certain number of times, divided by the action of some finite group. So what's going on here is here's a maximal torus. And in order to speak in concrete forms, let's imagine that G is embedded inside some unitary group. For example, here it already is embedded in a unitary group. In such a way that T can be taken to be G intersection with the diagonal matrices, a bit like what we had earlier on, except now we're doing it in the compact world with, of course, unitary diagonal matrices rather than positive diagonal matrices. So you can always embed G in UN in such a way that the diagonal matrices constitute a maximal connected abelian subgroup, a maximal torus, which is also a maximal abelian subgroup. And, oh, and I need to say what W is. It's just the most obvious thing. You take the group of the elements in G which conjugate the torus into itself, which conjugate diagonal matrices into themselves. Among those are the diagonal matrices themselves, and you form this quotient, and this is some finite group. If you think about the case of SUN and you ask yourself when can a matrix conjugate the diagonal matrices into itself, then you can easily check for yourself that only happens when the matrix is a permutation up to some signs. It is a permutation matrix.
so what's NLT again?
The normalizer, so.
Thank you.
set of g's such that g G inverse. Yep, let's keep it like this. So what this means that according to the philosophy, representation theory should be sort of the same thing to what? Well, we're supposed to study functions on the set of conjugacy classes, which is the same thing as functions on T modulo W, which is the same thing as W invariant functions on T. But a function on a torus is given by Fourier series. So what's going on here is that we should be studying something like permutation invariant Fourier series. Studying what happens when you impose on a Fourier series some condition that the coefficients, the Fourier coefficients, should be permutation invariant. And of course, that's exactly what happens. That's what Weil discovered. And he did so using the following device, which is going to use several times. Yeah. Let's consider the conjugacy class map. Let's take G, or if you like, it could be G. Maybe I should do it like this: G modulo T times T. G, which sends a coset and an element T like this, just to the obvious thing, GT, G inverse. So one of the things you learn, I guess it's more or less obvious from the definition, from the fundamental theorem. I didn't mention that this maximal torus is basically unique up to conjugacy, and it follows from that that this map here is surjective. Yeah. It's a smooth map of manifolds of the same dimension, and it turns out, so therefore it has a degree, and the degree turns out to be the W. And you can work out the calculus of this map suppose I have a function and I want to integrate it over G, like this. Well, I could introduce coordinates, so to speak, in this way and integrate the function first over a conjugacy class, and then integrate over all T's, which label the conjugacy classes, up to W. And, well, it's a W-fold covered, so you need to stick in a W like that. And so here's what we're going to do. Oh, I should say I didn't write this down. One more thing about this map. Here. This is a G equivariant map. G is acting on the right by conjugation, and it's acting on the left on G mod T just by translation. And the way things are set up, the conjugation action of G over here matches perfectly the left translation action of G over here. So this is a G equivariant map. And it means that when you study the Jacobian in the change of variables formula, it's not actually going to be a function of G, it's just going to be a function of T. It's going to be constant on conjugacy classes. So it's just going to be given by some function here, T. And here we integrate over the conjugacy class. Because everything is compact, rather than integrating over G mod T, you could just integrate over G if you wanted to. Simplify things a little bit. And so we have some formula here, and just a couple of remarkable things about the formula. So first of all, this Jacobian, this determinant of a derivative, is easy to actually calculate directly. And that's the basis of the subsequent observations. Well, first of all, whether or not you calculate it, just on theoretical grounds, you certainly know that this is it's a function on the torus, and this finite group W is acting on the torus by automorphisms of the torus. And this thing is a W invariant function. And let's suppose that we normalize the integrals in this way. That's the obvious thing to do. Choose Haar measures so that the volumes of both T and G are 1. In that case, now you can calculate explicitly what's going on here. And what you find is that this is well, this doesn't depend on the normalization. It's a polynomial function of the diagonal entries of T. Remember, T is a group of diagonal matrices. We decided to coordinatize in that way. So it's some polynomial function of the end, of big N diagonal entries that you see in the definition of T. And now this is where you need to calculate, and so this, what I'm about to say is very special to compact groups, and it's strictly speaking not necessary, but I'm going to tell you all about Weil's theorem just for fun. What's interesting about this function is it has, this polynomial function is it has integer coefficients. As far as I'm aware, that doesn't follow from purely theoretical grounds. I mean, you actually have to calculate what this thing is, and this is what you discover. And there's one more fundamental thing. It's so fundamental. Put it here. And okay, so what you have to do is let the group be SU3 or SU2. But SU3 is more convincing. Let the group be SU3 and just do the calculation. And then you'll see that Hermann Weil is right. This function actually has a square root, sort of holomorphic square root like that. So this guy is also a polynomial, just to make it challenging in the entries. Of T. And it's also W invariant. Well, not quite. It has a very interesting property. It's W anti-invariant. The elements of W are automorphisms of this torus, which is an oriented manifold, and some of them flip the orientation, and some of them don't flip the orientation. And if you have an element which flips the orientation, it also actually flips this function to its negative. That's what I mean by anti-invariant. There's a polynomial in entries of G. Oh, I forgot to say one. And, should have said this the other way around. Again, integer coefficients. In the case of SU3 or SUN for that matter, you can just calculate and you can see that this is true. Actually, you have to be a little bit careful. There's a topological obstruction which has to do with two torsion in the fundamental group. So this is not quite true in general. It is true for SU3, SUN. But there's a small subtlety that we'll talk about later. But it's basically true. If it's not true for the group, it's true for a double cover of the group. So, and that's also a compact connected Lie group. So it's a small point, and it's so small that I don't want to talk about it anymore, except to be honest and say that this point exists. But for SUN, for example, or UN, you don't need to worry about this footnote. Okay. And so, suppose you look at functions on G, which are functions just of the conjugacy classes alone, so-called class functions, which are invariant under conjugation. If you have a function which is invariant under conjugation, this formula simplifies, of course, because you're just integrating a constant function here. And so what you see is a formula relating a function as it is defined on G, which is a class function, to the restriction of the function to the torus. Those functions have the same integral, not quite because of this factor delta. But this factor delta has a square root, that's what I just said here. And so you get a unitary isomorphism like this. What you end up with over here are the L2 functions on T. You multiply, so what the map is you take a function, you want to preserve the L2 norm, you have to multiply it by the square root of the Jacobian, the square root of the Radon-Nikodym derivative. So you have to do that. So if you started off with f and you restricted it to t, of course, you'd have a w invariant function. And then if you multiplied it by an anti-invariant function, it would become w anti-invariant. And that's what this minus sign means up here. That's just the pointwise product. Okay, this is such a nice, you know, of course many of you already know this, but I took a survey at the beginning of the class and I asked how many people knew this, and very few people admitted to knowing it. So that's why I'm going through the details. This business here of the Weyl integral formula, this we'll see, again, it's rather important to understand that you can establish these formulas, and it's just a mechanical thing. You want to calculate what this Jacobian is, well, pick up a calculus book. It's not hard to work out what this thing is, and it's always just a function in this kind of context, a function just of t, which labels the conjugacy classes, not of g, which labels the conjugation. So this is a very general formula. This is called Weyl's integral formula, unsurprisingly. And so we definitely will, we'll see other examples in just a moment. Maybe not just a moment, in the afternoon we'll see some other examples. But here it's really amazing what happens. This is the world's single greatest, in my opinion, application of the definition of Hilbert space. This is just the most beautiful thing. Here's what Weyl observed. So note or no. If you have a representation, then you can build its character, which, let me just remind you, is this function on G. And if you look at the characters of irreducible representations of G, it turns out that they all have L2 norm 1 under this normalization of the measure that we had up here. That's called shear orthogonality. And as another part of shear orthogonality, they're orthogonal to one another. These guys form an orthonormal basis. And if you ask what these functions are when you restrict to t, which is a subset of g, they are polynomial functions in the entries of t with integer coefficients. In fact, positive integer coefficients. That's because if you have a representation of g and you restrict it to t, you can diagonalize the representation. You can write it as a direct sum of one-dimensional representations, and this trace will be a sum of traces of one-dimensional representations. In other words, just a sum of unitary characters, but the diagonal entries of T obviously form a generating set under multiplication for the unitary characters. So this is just this piece of cake. Okay, great. So if you take the characters and you multiply them now by delta, you get a basis of the same type. Except, of course, these ones here were W invariant. Once you've done this, now they're W anti-invariant. And now, of course, we're on the other side of that map. Let's say for the right-hand side of the map star. Like that. Nearly done. It's the incredible theorem of Connes-Kasparov. In the unlikely event that you really haven't seen this before, you absolutely have to do this for SU3 and see it actually work out, because it's so incredible how beautiful the whole thing is. So there's a but. In fact, this Hilbert space, so there was a 1 over W, I forgot to mention that, but in the integral formula, there was a 1 over W. So at this point, you need to adjust the inner product by a numerical factor of W. I forgot to enter that up there at the top. So now we ask for an orthonormal basis of this Hilbert space consisting of polynomials in the entries of T with integer coefficients, and which is W anti-invariant. Okay. Well,
so that's what minus W means.
That's what minus W means, anti-invariant instead of invariant. And so you ask yourself so you start to see what could the possibilities be. We know how to get an orthonormal basis for L2 of T, the unitary characters themselves. Given an orthonormal basis for T, the monomials, the trigonometric monomials, they're a basis for L2 of T. If you want to enforce W anti-invariant, you have to form alternating sums of trigonometric polynomials, of trigonometric monomials, and that's it. Those that now form an orthonormal basis for this space here, which are W anti-invariant, and they're the only ones. If you think about it for a moment, there are no other possibilities with the constraint of having integer coefficients. The only possible thing you can do is take a sum over W of W applied to phi. Phi is a single unitary character. Alternating sum. Minus 1 to the W, which means plus or minus 1 according to whether W preserves or does not preserve orientation. Well, there are some signs. You can, in any orthonormal basis, you can take minus a vector and it's still a member of an orthonormal basis. But that's it. That's all you can do if you insist on these conditions for the entries. Okay. So this is one basis with all of the good properties. This is another basis with all of the good properties. And there's only one basis, so they're the same. Let's call this the alternating sum associated to phi. So if you like, if you have a character of an irreducible unitary representation, a trace like this, and you restrict it to the torus, of course the torus intersects every conjugacy class, as I said that earlier on, then there's a formula for what this is. Namely, it's just the alternating sum of phi evaluated on T divided by this Val denominator. And I won't say what it is for SU3, but for SU2 you can now work out exactly what's going on. So let's say T is the diagonal matrices as we were discussing. Maybe I'll make this a little more explicit. All matrices of this form. Inverse or blue bar, whichever you like. All of the characters look like this. We take a unitary character of the circle, it's that, and we anti-symmetrize. That gives us that, and now you have to calculate what this denominator is, and it's z minus z inverse, and that's it. And any n is allowed. Something happens here, which is that if n is equal to 0, you get the 0 function, so that is not, in fact, in the basis. But as long as n is not 0, these are the basis elements. There's a redundancy in these, because if I replace n by minus n, I get basically the same thing, so I should let n be positive 2. So you can work out what this is. It's z to the n plus 1 plus z to the n minus 1 plus z to the n minus 3 plus blah, 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 all the way down to z to the minus n. So that's the beautiful theory of file, which we'll see again in the afternoon. And it's just the most spectacular application of Hilbert space theory. There are lots of much more complicated applications of Hilbert space theory, but they don't get any more beautiful than that. Okay. Any questions? I'm about to return to non-compact groups after this little reminder, this little enjoyment. You see, if I didn't plan that we should stop and take a break, but this is like a break. The Val character formula, it's better than taking a holiday is to read about the Val character formula. It makes you feel good to read this particular piece of mathematics. I think my break is better than your break. You know? Now we feel good because this is such a wonderful thing. Okay, so back to, for a little while, back to non-compact groups. So we have the Val character formula available to us whenever we might need it, and we have some crucial ideas related to the proof available to us, for example, the integral formula, and don't forget them. But let's go back to non-compact groups, and let's think about the philosophy. And so if you want to understand what G looks like up to conjugacy, it's a little more complicated. But it's still a tractable object, as I'll show you. On Jew. See? But still, as we would say in English, tractable. It's not too bad. It's still not too bad. And let's just look at an example, see if we believe that. Suppose G is the group of 2 by 2 matrices. So G itself, I think we discussed this at some point, it happens to be the same thing as SU11, which is a better set of coordinates. And what G looks like itself is a torus. So the cross-section of this torus is a solid open unit disk. And then, of course, it's a solid open unit disk times a circle. Oh, I guess you can see what the structure is. The circle is SO2, and the solid disk is the Poincare disk, G modulo K. So G is, roughly speaking, K times G mod K. In fact, topologically, it is K times G mod K. And the G mod K is the disk direction, the slice through this torus. And the K direction is going around. So it's an open torus like this. And somewhere in the open torus is the identity, like that. And so that's a matrix, and it's a matrix whose eigenvalues are 1 and 1. It's the identity matrix. It has one eigenvalue with multiplicity 2. And moving away from this identity, there are a whole bunch of matrices which are all matrices which have only the eigenvalue 1. So these guys here are all matrices with, well, all unipotent matrices. Both of their eigenvalues are 1. Okay. And they sort of go off and around. Here's -1, and then over here we have the negatives of the unipotent -1. The negatives of the unipotent matrices like that. In order to see what else is going on, let's take this picture and let's take the logarithm near the identity matrix. We can take the inverse of the exponential map, and then we're in R3. And this space of unipotent matrices is just the right circular cone that we were looking at before. Here's the identity. And so outside, the region outside consists of matrices with real eigenvalues. And the region inside consists of the matrices with unitary eigenvalues. I'll just say imaginary. Of course, some of the eigenvalues is 0, because these are traces of matrices. And so there are two different qualities that a matrix can have. Either it can have real eigenvalues, or it can have imaginary eigenvalues. And the interface is the matrices where the eigenvalues are, well, in this logarithmic picture, where the eigenvalues are 0. These now become nilpotent matrices after you've taken the... Oh, I see, this corresponds to this. So this is nilpotent, is unipotent. So that's what the geometry is. And all of the unipotent matrices are conjugate to one another, pretty much. There are two conjugacy classes, and then there are two more conjugacy classes over here. And it's complicated what's going on here, because these conjugacy classes are neither open nor closed. All of them, these two, contain in their closure the identity. On the other hand, the rest of the picture is very, very easy. So just to continue with SL2 for fun. So is the right word. Now you do a little bit of calculation. Well, you use linear algebra, I guess. If you have a matrix with real eigenvalues, and if the eigenvalues are distinct, then the matrix, of course, is diagonalizable, because the multiplicity of the eigenvalues has to be 1. And in fact, the diagonalization can be done by an SL2R matrix. So everything outside here, or outside these cones in this torus picture, consists of matrices conjugate to real diagonal matrices. And in a similar way, everything inside the cones consists of matrices conjugate to SO2 matrices. So we have these two maps now, we could take G modulo T cross T, and then take the disjoint union of that with G modulo H with H. We were calling it L. Let's stick with L here. So the map here is the usual thing, so GT comma T goes to GT G inverse. I'm sorry, I called it T. It is a circle group, it is a torus, but the notation that we have established for ourselves is K. In this particular case, K is an abelian group. And same thing over here, of course, GL comma L. G inverse. So this is a map which has open, dense range. In fact, the complement of the range is exactly the unipotent matrices. The range is some subvariety of lower dimension. So the complement has measure 0. As far as L2 is concerned, you can forget about the matrices which are not conjugate to one of these two subgroups. And so we have two geometrically very, very nice maps which account for almost all of G, but not everything in G, because you have to throw away the unipotent matrices. So G modulo conjugacy is equal to, well, it's not so bad. It's equal to K. Union L, as it happens, there is a vowel group here, two-element group. There is, as it happens, no vowel group here. Union, a small amount of other stuff. And it's small in the geometric sense that all of the other stuff lives on subvarieties of submanifolds or singular submanifolds of lower dimension on this cone. And it's small in the sense of measure theory. The measure is 0. So it's not bad. It's not bad. And so we have a right to expect that the representation theory will not be too bad. It will involve functions on L, and it will involve functions on K. And functions on K is all about Fourier series, some discrete parameter. And functions on L is all about Fourier integrals, the Fourier transform. So that's some continuous parameter. And that, indeed, is exactly what we saw when we discussed the representations of SL. All right, so that's just encouraging that we should be able to deal with a slightly more exact parameterization of representations, because we've just dealt with the parameterization of the conjugacy classes. It works out perfectly, except for this business here, and now you have to worry, is this cone going to cause you problems, or is it not going to cause you problems? And okay, one doesn't know until one does the calculations. So this, of course, was all perfectly obvious to Harishchandra. And now I want to return to transfer, or, excuse me, parabolic induction. Which we discussed at the very beginning. So I don't know, maybe transfer sounds friendlier than parabolic induction. One of the things I don't like about parabolic induction is that there are no parabolas in parabolic induction. There are lots of hyperbolas, lots of hyperboloids, but no parabolas. So it's a shame that it's called parabolic induction. So we thought of it as star homomorphism, actually one of these correspondences, a generalized star homomorphism like this. And you can ask the following question. So now we want to classify the representations of this fellow. what are the representations of this fellow? Well, we made a guess based on the conjugacy classes about what's going to happen for SL2R. But in general, we might ask the following thing. Is it ever the case that every representation of G is accounted for in this way? In other words, in C-star algebra speak, is this morphism so for a given L, so by the way, I'm back to talking about a general group G here, so it's the end of the discussion of SL2. Is this morphism ever injective? Ever one-to-one? If it is one-to-one, that means, when you translate from C-star algebras to representations, that means that every irreducible representation of G embeds in some irreducible representation as a discrete summand of an irreducible representation transferred from L, or if you like, parabolically induced from L. And as we discussed, ultimately, that means it embeds in a representation parabolically induced from some discrete series mod center representation of some Levy subgroup of L. So everything will come from transfer from a smaller group. Sounds like a bit of a paradox. Why can everything really always come from something smaller? Well, yeah. And so it's an interesting question, and we can guess the answer based on this philosophy. And the theorem of Harish-Chandra is that the guessed answer is correct. Let's state the theorem, the wonderful theorem of Harish-Chandra, and then take a break. And we'll return to Hermann Weyl in due course. A reasonable guess, based on the philosophy of conjugacy classes, is that this sort of thing is going to work. There will indeed be an injection here if L accounts for all of the conjugacy classes of G. If everything in L, every element of the group G is conjugate to something in L, then we're in good shape. According to the theory of the philosophy of conjugacy classes, we should be able to see from the perspective of L everything over here in the world of G. And that's what the theorem says. In fact, you don't have to worry about this awkward stuff here. So we could take L and we could saturate it under conjugation inside of G. It's not, well, let me just say dense here. It's dense range. This is a complicated map because of these singular conjugacy classes, and the range of this map is not open. So it's a little bit complicated to think about what the geometry is of this range, but we'll come say a little bit more about that in due course. So this is the hypothesis which is connected to the philosophy we were discussing, but you can work out when this condition actually happens. If G is a connected group, and if G is a connected group, then K, the maximal compact subgroup, is a connected group, and so it has a maximal torus. V or A maximal torus. better job. Maximal torus T. Okay. So the condition, so you do a little bit of group theory, which, as I explained at the beginning of the lecture, is basically linear algebra, because these groups are basically linear algebraic. And the condition is that this thing here should have compact. Sorry, what I'm going to write here is indeed for groups with compact center. Compact centralizer. So there's nothing, there are no one-parameter subgroups, positive, definite matrices, nothing like that, which commute with T. That's it. Okay, screwing myself up here. But for example, SL2R has this property, but SL2C does not. If you take SO2, there are no matrices which commute with SO2 inside of SL2R, which don't already lie inside of SO2. On the other hand, inside of SL2C, the maximal torus are the unitary diagonal matrices, and there are lots of other diagonal matrices which are not unitary diagonal, and they commute. So that here the centralizer is non-compact, and here it's compact. And now I have to dig myself out of a small language problem. This is not the hypothesis. This is the conclusion to a theorem. So no, I just said equivalent. Okay, good, it's fine. But now I've screwed. Okay, I remember the problem. Let me just try and. My apologies. I have the things screwed up as not this property, as it. And, terrible, terrible, terrible. There exists such an L. And only if this property holds. Let me try and.
So there is no equivalent.
Yeah, let me try and say this better. I'm hypothesizing that there exists one of these block diagonal subgroups, the Levy subgroup, which has the property that when you saturate it inside of G, make all of the conjugacy classes G conjugacy classes instead of L conjugacy classes, that when you do that, you get a dense subset of G. Now you can ask, when is this ever possible? And as it happens, this condition can be satisfied for some L if and only if this maximal torus has a non-compact centralizer. This is the criterion. If the centralizer is compact, there is no such L. If the centralizer is not compact, there is such an L. My apologies for such a horrible way of explaining it. The existence of such an L is equivalent to the existence of a non-compact centralizer of the maximal torus. My apologies. The theorem is that for such an L, transfer map means that for such an L, if it exists, every representation of G is accounted for by parabolic induction by transfer from some representation of L. And you don't have to look anywhere else. There are none of these discrete series at all. In the case of a complex, let me not say anything more because I already went on long enough. We shall discuss this better, I hope, and more clearly after lunch. So I will spend some time trying to recover from this poor presentation. And then, of course, my duty is to try and explain why this is true. As we try to understand this theorem, we'll have to think about Monsieur Plancherel. We have to think about not Hermann Weyl, but Plancherel. It's Plancherel whose ideas are relevant for the proof of this theorem. So we'll do that, and then we'll turn to the situation in which no such L exists. In that situation, it's a theorem, another theorem of Harish-Chandra, that there are discrete series representations. And we then have to discuss how to understand those discrete series representations. And finally, at that point, there will be Dirac operators. Okay, now is an excellent time for me to stop talking. So thank you very much.
Any questions or comments? So the lecture will continue in the afternoon also. So if you have comments or questions privately, you can ask.